So we have another problem here. Let's see how we do. I'm on my crusade here to try to solve as many problems as I can, but it seems that more than 5 or 6 a day is going to be a challenge. I don't know. I guess once I really get going, it'll be. Actually, I don't know. Let me not say one way or the other. I think some of these problems will be easier than others, but some of these are just going to always be challenging. But here we go. Minimum in rotated array, sorted array 2. Okay, let's try it. Okay, how do we do? Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, the array num 0, 1, 4, 5, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 4 if it was rotated 4 times, and if it was rotated 7 times, it would be right back to where it started. Rotating an array one time results in this array, right? Given the sorted array nums that may contain duplicates, return the minimum element of this array. You must decrease the overall operation steps as much as possible. Minimum element of this array may contain duplicates. So the previous one didn't contain duplicates. The previous solution didn't contain duplicates. I kind of want to look at my previous solution, but I think the way you do this is a logarithmic search. But the problem is you don't know where this breaks into 2 different sequences. It's a lot easier if it doesn't have duplicates. Similar, but nums may contain duplicates. Affect the runtime complexity, how and why. Since n is only 50,000, you can do this in linear time. The minimum element of this array. So you can do this in linear time to get the minimum element with only 50,000. But with duplicates, I don't actually know. So the idea is to do it in logarithmic time. I'm curious to see if they have like a time limit on this that'll, that would be appropriate. So what's interesting about this question is you can do this. It's interesting that they use a reference initially. So you can do this very quickly. All right, let's just say int ret equals 0 for const int x in nums. Say ret equals standard min of ret and x. Return ret. Forgot one detail. Include. Oh, actually, you can even do. There's even. Yeah. Do one even better. Standard. There's at least one element, right? Yeah. Standard, and it's just min element of nums.begin, nums.end. I think that's all you need really. And this should run in. This should run fast enough. Yeah. So interesting question. Obviously, we didn't really solve it. We just kind of just like without thinking too hard about it. We just went for it. But the idea is to do this in logarithmic time rather than now. If there are no duplicates, I think you can do this in logarithmic time relatively easily. If there are duplicates, then I think you're stuck doing this in linear time. I don't think you can use. I don't think you can use the previous algorithm that I used. I don't think that you can use the previous algorithm that I used, and also the problem you run into is can't use the previous algorithm, and the algorithm that you would use for this, I don't know. So let's chat about that for a moment or two. What could we use to solve this? And obviously, you see, only 11% of the solutions use what I used. That's interesting. It's interesting. So, let's ponder this for a moment. Let's think about it. So what could you do to solve this more efficiently? Well, ultimately what you'd want to do is find out where the split is in the array, in the sorted array, and if you can do that, then you can just perform a logarithmic search over the two. So in logarithmic times, you can find the split, how many rotations there were or are. Then you can just break the array into two pieces and perform a logarithmic search for the smallest element. Actually, it should be the first element from both. You just compare those two minimum elements. Now there might be a way to do this that's a little bit easier, but yeah, you'd want to do this in logarithmic time. That's the idea. And it's just it's a simple. It's actually if the arrays are sorted, it's not even logarithmic. It's the first. You would want to find out where they're split in logarithmic time, but also you could say. You know, what's interesting about this is, so if it's, the minimum, so what's interesting about this is it's not just two sorted arrays, by the way. It's actually this the sequence, the sorted sequence split into two pieces. So one of these sequences, all of the elements are smaller than the other sequence. Right, and you want to figure out which sequence is, I guess, the first element, which one that's a part of, if it's a part of the whole array. So actually, you can do this. You could check the first element and the last element against each other, right? So if you're totally sorted, the first element will be smaller. If you're not sorted, though, the first element should be larger, right? And the reason is that the first half of your array is going to be on the right side. Let me see. Is that right? If we go back to the description. Yeah, first half of the array is they're rotating. There's to the right would be clockwise, to the left would be counterclockwise. So to the right, if you rotate 4 times, you're rotating to the right. So yeah, that means that here's the problem though. If there's duplicates, then these elements won't necessarily be different from each other. They could be the same, and then you have a problem. In fact, if they're all the same, then you have issues, right? How do you figure out the smallest element if they're all the same number? Is it possible? I don't think so. No, I don't think so. If there are duplicates, I don't think there's another way to do this, quite frankly. Quite frankly, I don't think it's possible to do this any other way. Nope. Because there's no, let's say you looked at every element except one, right? So you could actually prove that it's not possible to do this better than linear time. If you looked at every element except one, and let's say they're all the same element, or possibly all the same. Let's say they're all the same up to that point, right? So the last element you haven't looked at. What would happen, and that could be true, because they could all be the same element, right? So let's say you looked at all the elements, they're all the same except for one. You haven't looked at one and you don't know if it's the same or not. If it's a smaller number than all the others, that'll affect your result. The larger number it won't. If it's the same number or larger it won't. But if it's a smaller number it will. So you need to look at it. Can you tell if it's larger or smaller? You don't, because you have no way of knowing how much the array was rotated, because they're all the same numbers. Who knows? And so there's no way to do this faster. Actually, this is it. This is the only way. It has to be linear. Let's see if we can get a better result though. There you go. Yeah, I was gonna say, I think it's just some of them got 8 milliseconds, some of them got 0 milliseconds, some of them got 4. Yeah, there's only one way to do this, is linear. That's just kind of a non-question here. We should look at another one. I spent a pretty good amount of time looking at this, but there's no way to do this faster if there's unbounded number of duplicates. Yeah. Let's look at the discussion quickly. Did this get a? This probably should get. Oh, got a lot of upvotes. Beats 100% binary search with explanations. Most likely has to be ON. Stop wasting your time. Yeah, I don't think it can be binary search. There's no way faster way than ON to solve an input. Which work in this case is your nums. Which half would you discard then? That being said, it's probably the only way to solve it. Runtime 6 milliseconds, not bad at all. Worst case, average binary search is still better. Yeah, but it's not. But you're looking for worst case. This is the worst case. Does it say they're trying to get the average case? Overall, as much as possible. That's not. What is the point of this? I mean, you can binary search, but it doesn't really work, right? Binary linear combination. I mean, yeah, you can make it a little bit faster, but it's not. It's sort of not meaningful, right? Because there's you don't know what your inputs are going to be, right? Like, I guess average case could be improved, but even average case is like arguable. How do you even? I don't even know what the expected runtime would be. How do you even analyze that? I mean, it's kind of infrequent, I guess, that you need to examine all of them, O of n. I guess most cases would be you could do a login with some binary search optimization. Okay, I guess, whatever. I don't know. You can kind of throw out the sections that are, or you can, excuse me, I don't know. You can maybe the sections that are obviously have the same values. Maybe you would do binary search on those, or not binary search. You would have to perform some linear search to make these smaller. So I guess what you'd have to do is you do multiple binary searches to try to like find any kind of different numbers. So it would be like multiple binary searches through the whole thing, which would end up being just a sort of discombobulated linear search, something like that. I don't know. I wouldn't know exactly what you would do, but you'd try binary searching, and I guess what you would do is I think the only thing you should do or could do is just left to right. You just have a sliding window until they're different, and then you can once they're different, actually you're kind of done there. because one's larger and one's smaller, and that denotes which one is the beginning of the larger one should be on the right side, increasing sequence. They're both increasing. The larger one will be on the right, the smaller one will be on the larger one will be on the left, smaller one's on the right, and from there, this should keep decreasing. This should keep increasing. Should be able to do a binary search, I guess, to find that midpoint after that. How does that work? Well, at that point, actually, I think you could locate it directly, immediately. You wouldn't even need to do a binary search because you know how many elements there are in your sorted list. And you know that because you know how many elements between the two of them there are, right? That tells you, yeah. So if you have two, let's say there's an element on the left that's larger, and an element on the left that's smaller, right? And you find that. That means it was rotated. That's the first thing. If it wasn't rotated, if that wasn't the case, if it was the other way around, the left one was smaller, you would just take that element immediately, right? That's the only case. But if you kind of move things closer and you get the same thing, right? Again, it was rotated. The deal is how much was it rotated is the question, right? I'm wrong about that. I think you do need to do some kind of binary search. You could figure, yeah, binary search would just tell you, if you just take the middle of the two, if it's larger than the left side, then that means it was on the left, still on the left sequence. If it's smaller than the right side, if it's smaller than the left side, that means it's on the right sequence, each point. And so if it's on the right sequence, you're gonna go down. If it's on the left sequence, you go up. And that when you're in your binary search, that's all. Throw out the ones to the left. Yeah, okay, that works. That works. So yeah. But I guess you just use sliding window until you find two things that are different. Whatever, it's fine. It's not really. This is like not really. I don't know. I don't want to be like mean to anybody. Olivia. Oh, she got it. October 22nd. Fairly recently. Yeah. 2 more lines of code. Only add on the while loop. Have overlap, remove the overlap. Okay. Yeah. Yeah. You can't really avoid the linear time. You can actually prove it, as I said. If you don't consider all the elements, it'll change your solution. All right, so let's move on to another one. That was like, I mean, I thought about it for some time, but all right. Anyway, so yeah, very good. Probably would be challenging to actually code it. I think I could do it, but I have enough practice with binary searches to do it. But I probably would struggle a little bit to code it. But that's like, I don't know. I always kind of struggle a bit when it comes to binary searches, like custom binary searches. Anyway, so yeah, thanks for watching. I'm gonna start another problem. We're just gonna do another one. I felt this one was kind of a little bit on the easier side. So yeah, let's do that. All right.